Imagine buying a new home with an approved yard, only to find that one short year later, your lawn has turned into a muddy swamp. This failure happens because local health departments rely on the standard percolation test. An inspector digs a hole, fills it with clear tap water, and times how quickly that water drains into the soil. A passing grade here creates a false sense of security. The test treats the yard as a physical hydraulic system, assuming the soil will always accept liquid as easily as it accepts clear water. During the post-war housing boom shown in this photographic source image, developers built millions of homes relying on individual septic systems. This massive, invisible infrastructure was the primary solution for waste management outside major cities. By the 1960s, the Federal Housing Administration faced a crisis of widespread, unpredictable septic failures. These breakdowns threatened their loan insurance program, proving that the established criteria for these systems were deeply flawed. To find a solution, the FHA commissioned researchers at UC Berkeley to investigate why systems that passed the percolation test were collapsing in the field. The team discovered a fatal disconnect in the test's design. It utilized clear water. In reality, a septic tank discharges effluent rich in organic nutrients and suspended solids. These biochemical properties mean a septic system cannot be managed like a simple drain pipe. It is a living environment where biology, not just physics, dictates the flow of water. The researchers separated the problem into two forces. First is percolative capacity, the speed at which soil transports water downward. On the right is infiltrative capacity, the soil's ability to accept liquid at the surface. This surface acts as the central gatekeeper. When nutrient-heavy sewage hits the soil, it triggers an explosion of bacterial growth. These microbes feed on the waste, creating a dense organic clogging mat of slimes and solids just half a centimeter thick. Continuous use of the drain keeps the system constantly inundated. This standing water displaces all the oxygen, allowing anaerobic bacteria to multiply and further seal off the soil pores. This oxygen starvation produces a specific chemical byproduct, a black particulate called ferrous sulfide. The ferrous sulfide deposits into the organic mat, turning the bacterial slime into an impenetrable cement-like barrier that effectively suffocates the soil's ability to accept any more liquid. In a standard trench, effluent pools at the bottom, forming a watertight black seal of ferrous sulfide. With the floor sealed, water rises, flooding the lowest inch of the sidewall. This newly submerged soil clogs and fails, forcing the water incrementally higher. The study called this incremental bottom-up destruction creeping failure. The system is essentially a rising tide of anaerobic sludge. Treating a percolation field like a static underground bucket guarantees this outcome. Eventually, there is no unclogged surface left, and the system collapses entirely. To combat this, the Berkeley team determined the system must be engineered to breathe. Recovery is only possible if oxygen can reach the clogged surfaces. Their first engineering criterion focused on geometry. Because bottom surfaces fail almost immediately, a system should maximize vertical sidewalls. Narrow, deep trenches provide more functional surface area per gallon of waste than wide, shallow ones. Gravity assists these vertical surfaces. Unlike a flat floor, gravity helps in stripping the walls of decomposing biological matter, allowing the upper pores to remain open and aerobic longer. The researchers also redesigned the trench fill. By grading gravel from coarse stones in the center to fine pebbles at the soil wall, they eliminated abrupt transitions in particle size. This forces the biological load to penetrate several inches into the gravel rather than hitting the soil as a single wall. This clogging in depth prevents the formation of an impenetrable surface mat. Distributing the bacteria through a larger volume of material keeps the infiltrative capacity high and sustainable. The primary operational fix identified by the researchers was dividing the entire system into two separate, isolated sectors. Wastewater is directed into only one sector at a time. The system is used until that sector reaches its creeping failure limit and can no longer accept the daily load. At point, the flow is manually diverted into the second, rested sector. This leaves the first sector completely empty and allows it to drain. As the liquid drains out, atmospheric oxygen floods back into the soil pores. This oxygen oxidizes the ferrous sulfide, converting the solid black barrier back into a soluble sulfate that washes away. This regeneration process requires months or sometimes a full year of total rest. This time allows the soil to fully dry and the aerobic bacteria to break down the organic mat. The 1967 study transformed underground waste management from a physical dump into a biological cycle. By allowing the soil to breathe, we are able to turn an inevitable failure into a sustainable, invisible ecosystem. Meet Larry Stevens. He's a professional engineer, and his career was basically the perfect storm for this invention. We're talking over 50 years of experience. He's designed systems, he's been a state regulator, and this is the important part. He owned a maintenance company for over 20 years. He was the guy getting the phone calls to go fix all those failing systems. He saw the same problem, that biomat clog, over and over and over again. And this is his solution. It's called the Verti-Grid. It is engineered specifically to make that 1967 research a practical reality. Water comes into the pipe at the top, and that grid design makes sure it spreads out perfectly over the entire vertical surface. It's then ready to be wicked away by the soil through that fabric wrap. So what you end up with are some major real-world benefits. The system often takes up less space, which is a lifesaver on tight lake lots and other restricted properties. It tears up the yard less, and the installation is faster and more affordable. And its versatility is amazing. This isn't just a fix for problem sites. It's an upgrade for any site, from a single-family home to a big commercial building or even a multi-home community system. So in the end, the Verti-Grid revolution isn't about some space-age technology. It's about looking back at solid science that we've known about for ages and finally pairing it with modern engineering. It's about creating smarter, longer-lasting systems that work with nature's own processes instead of constantly fighting a losing battle against them.